Welcome to Spirit of Maths. In this video, we will introduce the cosine and sine of a square matrix, and actually the exponential of a square matrix is well known and can be used to solve some ordinary differential equation, namely the equation x prime t equal a xt. But the cosine and the sine of a square matrix is less known, and in this video we will introduce these two notions. We will show also that we still have the same identity as when a is a real number, and we will use the cosine and sine to give the solution of this ordinary differential equation. Okay, so let's go. First, we recall that for any x in R, the cosine and sine of x have a power series expansion, namely cosine x is equal this infinite series, the sum from 0 to infinity minus 1 power k x power 2k and the factorial of 2k. And we have a similar formula for sine x. So moreover, we know that the solution of this ordinary differential equation is given by yt equal a cosine rt plus b sine rt. Okay, so now with this remark, we can use these two formulas to define the cosine of and the sine of a square matrix. The idea is to see that here we can replace x by a matrix and also in this equation. So we we take a square matrix and we put by definition the cosine of A is the sum from k equal to 0 to infinity minus 1 power k a 2k over tk. What we have done, we have just replaced in this infinite series, we replaced x by e, and we do the same for sine. Now the question is to show that these two infinite series are actually convergent. It's not clear from the definition. So let's show that these two infinite series are actually convergent. Okay, so we start by the series defining the cosine, and to show that we will show that it is normally convergent. So we take a multiplicative norm on M and C, where M and C is the vector space of square matrix. A multiplicative norm means that the norm of AB is less or equal to norm of A time norm of B. Such norms exist, there are many such norms, and actually all the norm in M and C are equivalent, so we can work with any of them. We take one which is multiplicative. Now we will have that the norm of this quantity, which is equal to 1 over 2k factorial, the norm of a power 2k, and by using this property we have that this is less than 1 over 2k factorial norm de a power 2k. So we have now to show the normal convergence, we need to show that the infinite series, this infinite series is actually convergent. And it is something easy to establish. This infinite series is convergent for any x in R by using D'Alembert's ratio test. The D'Alembert ratio test, we will compute the limit of un plus 1 over un, and if we do so, if we compute the norm of uk plus 1 over uk, we get that this limit is equal to 0. This is less than 1, and the D'Alembert ratio test tell us that this infinite series is convergent for any x. And how this series is convergent, and we have the normal convergence of this series, and we know that the normal convergence implies the convergence. And finally we have shown that cosine A is well defined. We can do the same for sine A. We just replace here by the expression of Cn, and we have down this cosine A and sine E are well defined. Now with this definition, with these two definitions, we will show this identity. We will show that cosine square A plus sine square A is equal to the identity. We will start by some particular case before tackling the general case. First, we take a diagonal matrix. We denote it by this formula. It's we know that A power k is a diagonal matrix also, with lambda 1 power k, lambda n power k. And if you compute the cosine A by using the formula, here you get the diagonal of lambda 1 to k, lambda n to k, and the sum will take the sum of all the lambda e, and we get this formula. Cosine E is a diagonal matrix with the diagonal term R cosine of lambda 1 lambda n. So we have shown that the cosine of a diagonal matrix is a diagonal matrix, and it's easy. And we can do the same for sine, and now the formula is easy to establish, because the cosine AOCAR is square is a diagonal, and you get cosine lambda e, cosine square lambda e plus sine square lambda e is equal to identity, and we have down. Another case where we can show the identity easily, it's the case where the matrix is diagonalizable. This means that A can be written as P, the inverse of P dP, where D is a diagonal matrix. Here also we have this formula A power k. If you compute A power k, there is a cancellation here. P times P minus 1 is the identity, and we get that A power k is P power minus 1 d k and P. And now if you compute the cosine E, you get here we can take P minus 1 here, and we get the formula cosine E is also diagonalizable, equal P minus 1 cosine dP, and the same hold of the sine. And now the formula cosine square E plus sine square E is equal to identity. It's follow easily from this case. But we know that all matrices are not diagonalizable. There are matrices which are not diagonalizable. So we need to show the property for the general case. Let's do it. For the general case, we take cosine square E, and we write here, it's by using the definition. I take different index to see what is happening. And now we use, here we have a product of two sum. It's the sum of the different product. So we will get A power 2P time A power 2Q, and minus 1P minus 1Q, and we get this formula. Now we will work on this formula to make it more simple, and we start by taking m equal p plus q. We take m equal p plus q, and we get this new formula. Here we have minus 1 power n 2p, and we take all the sum over all p and q equal to m. Now we can take q equal m minus p, and we get now this formula. We have now just m and p as index, and in this quantity I will introduce the binomial coefficient by dividing here by 2n factorial. We make here 2n factorial, and we divide by 2n factorial to get the binomial coefficient. And now we have a beautiful formula for cosine square E. We do the same for sine square A. So here we take m equal p plus q plus 1, and we get this formula, and now we replace q by m minus p minus 1 here, and here we must make minus here because we have p plus q equal m minus 1, and here we get minus 1. And finally, the same, we introduce the binomial coefficient and we get this beautiful formula. And now we can compute the sum of these two formulas and we get this formula. Now we will show that actually this quantity is equal to 0. And this is a consequence of the Newton binomial relation. So we use the binomial theorem and we get that this quantity indeed is equal this quantity, and this by the binomial theorem is 1 minus 1 power 2m, and this equal to 0, and we have done. And we have shown that cos² E plus sin² E is equal to the identity. Now we will show two important formulas. The derivative of cosine t A is equal minus A sinus sine t A, and the derivative of sine t A is equal to A cosine t A. So let's start. We will show this one. This one can be shown in the same way. So if we derive this quantity, here we derive t power 2k. So we get the derivative of t power 2k is 2k t power 2k minus 1, and we will simplify here and we get equal here 2k, we write it a power 2k minus 1, we get a here, and now we will show that actually this formula is just sine t A. So we will make a change of parameter. If I change k in k plus 1, instead of starting at 1, we start at 0. Here the case k equal to 0, it gives 0, so here we take k equal to 1. So we get this formula, and now we compute this quantity, which is equal to 2k plus 2 minus 1, which is equal to k plus 1, and we get that is equal minus here because we have minus here, and it is equal to minus sin A, not sin, minus sin A. And we have shown this formula. For this formula, we can use the same computation. It's easy. Now we consider this ordinary differential equation where the unknown is a function from the real line to Rn, and little n here, we take here a little n, and we with the initial condition u not v not, and we will look for a solution of this equation in this form: cosine tb a plus sin tb b, where A, B are vector in Rn, and the capital B is a matrix. So we derive first, and we use the two formulas we have before, and we get this one. And now if I take the second derivative, we get minus b square xt. So this will be a solution of this equation if and only if a is equal u naught, capital B is v naught, and b square equal a. So it is well known that if we have a matrix, we can always find its a square of this matrix by solving this equation. The square will not be with the real coefficient. It can have complex coefficient. In some particular case, we can get the solution easily. For instance, if A is symmetric, a symmetric matrix has always a square, so we can take B the square of A. And now this condition, for instance, if capital B is invertible, we can take B equal the inverse of B not 0. So in many cases we can find this solution, and here we have done. Okay, so now to support the channel, please like, subscribe and share, and thank you.